Okay, guys, let's get started. I'm Owen O'Malley, and this is a talk about the file format benchmarks, comparing Avro, JSON, ORC, and Parquet. Who am I? I've worked on Hadoop since 2006. I've worked on MapReduce, Security, Hive, and ORC at various points. Actually, I worked on a bunch of other stuff too, but that's enough. And in particular, I've worked on a lot of the different file formats. I've worked on sequence file, RC file, ORC file, T file, and Avro. Okay, trick question. Does anyone know where T file is, or what it was? It's actually a file format that's in the Hadoop code base that no one uses. Okay, so what the goal of this was I wanted to do a science experiment because I mostly have worked on ORC, and I wanted to find out what the different file formats did well and what they didn't do well. I'd been to some presentations, and they always used like 10 meg of data. I was like, 10 meg of data is not enough to show anything. You really need to process a lot more data than that. And you want it to be open source, right? You want the results to be repeatable. You want people to be able to look at what you've done, make changes, suggest improvements, and look to see, in fact, what the results are in different conditions. Because conditions that happen in one set of hardware aren't necessarily going to be repeatable. Another problem I'd seen was that a lot of companies use TPCDS, which is a really good benchmark in terms of the queries, and it really sucks in terms of the data. They picked data that would compress insanely well. I don't know what they were thinking when they laid out the data like that, but it was really bad. And so I wanted to use as much real data as possible. And of course, I wanted it into the Apache projects. All right, so let me talk a little bit about the different file formats. So when we were working on Avro, the original, what we had at that point was called sequence files, and a lot of you are probably still familiar with sequence files because it was the default MapReduce file format for a long time. It did really well, it was really efficient, but there were two problems with it. The first is that it was completely Java specific, right? You just had one kind of data there, and you had no way of evolving your schema. So if you suddenly decided, I need to add a new field to my type, you were completely screwed. Actually, there were some hacks, but they were completely hacked. And so we designed Avro to be evolvable with a schema. Now, during those discussions, actually, one of the people who was in the design discussion worked at Google, and he actually, at that point, Protobuf wasn't even released as open source. And so he actually made a call when we were like, gee, it'd be really nice if Protobuf was available. He actually made a call, and that's why we have Protobuf available today. But Avro, we designed it so that there is no information, no metadata about the record in each row. So Protobuf, you've got some of the data metadata about the type outside, and some of the type inside. Same with Thrift. But with Avro, all the metadata for the schema gets pulled up into the top of the file. It actually makes it work really well for files because you just get that metadata once instead of repeated. The one piece we really messed up was we made it a row major format, because often you need to read some of the columns, but not all of the columns. And if you have 200 columns and you only need 2 of them, having a row major format means you read all the bytes. And that's unfortunate. All right, now, at first I wasn't going to include JSON because it's very different from the other ones. But so many users are like, we want to store JSON in our Hadoop documents, our Hadoop clusters. And so I wanted to put it in. There are a lot of advantages to JSON. There's an incredible number of parsers. You can read it in any language, write it in any language. A lot of web UIs and REST UIs produce it, and it's text, so you can read it. And it's very, very common, right? No one will get confused if you give them a JSON document. Additionally, schema is completely integrated with the data. So kind of the reverse of Avro, where the schema all moved to the top of the file. Here, all the schema is in each of the records. So when you're looking at a JSON file, you actually have to read the whole file until you have any idea what the schema for that file is. It's usually compressed at the end, right? There's no way of compressing individual records, which for Hadoop type workloads and Spark type workloads, that's really unfortunate because that makes it very difficult to split the file in the middle. Okay, so we had these file formats. There was also ORC file in Hive. And we wanted to make a better file format. And so part of the problem with RC file was that it didn't have any understanding of the data that was actually inside the file. It was just storing binary blobs. So yes, it was column major, but there were binary blobs inside. So there was no way it could know, hey, this is a 1 followed by a 2. Maybe I could use fewer bits than 16 or 64. So there was no way of doing that kind of analysis because you didn't know what type it was. So we designed it so that it was columnar, of course, and we separated the schema and put it into the footer. Actually, all the metadata for org file is in the footer. Why do you think that is? Come on, someone ask me a question. Someone come up with the answer. Why would we have designed org with the file information in the footer instead of the header where most files put it, the file information? Yes? Exactly. So he said the number of records, you don't have any idea. But actually, there's a lot of information that we collect as we're writing the file. And because HDFS, you can't change the file once you've written it. It's much more convenient to put it at the bottom of the file rather than the top, because you can keep the information in memory and then put it down at the bottom where it's very easy to find, but still available. We also have a rich type model, so it can store complex types, it can store structs, it can store lists, maps, unions, all of those types can go in, and it's got integrated compression, indexes and stats. So what that means is that for the file, you store the min and max for each column, how many values it has, how many, whether it has nulls or not. You also store that for the stripe and at the row group level, which is every 10,000 rows. And you have indexes so that you can jump to the beginning of every 10,000 rows. We'll see why that matters in a bit. While we were designing org, Twitter and Cloudera were designing Parquet. And unfortunately, neither of us were talking to each other, and so we released them both into the wild at the same time. It's more directly based on Google's Dremel paper. Dremel was a processing engine that did some high-level query processing. The schema is also in the footer. So it's very similar to org. The main differences are that the type model is very high level with implementations, implementation-specific types. So the physical type will be something like an int 96, and you don't know what that means, the value is. So one of the possibilities for a logical type would be timestamp, where in org you'd know, okay, that's a timestamp column, In Parquet, it's an int 96, and with a hint that, hey, the user probably meant a timestamp here. One of the interesting pieces here is that the information about whether you have nulls or repeats, in ORC, you can think of the type structure as a tree with the number in the middle as to how many values in a list. With Parquet, all that information is pushed to the leaves. In practice, that doesn't change very much, other than it makes the Parquet reader a little better for highly complex types and a little more confusing if you try to jump around. All right, so one of the pieces, so those are our 4 file formats, and I wanted to try a set of different use cases, because part of what happens with this kind of analysis is that different use cases behave very differently, and in particular we wanted to look at as many real data sets as we could. So fortunately, every time someone takes a taxi in New York, and those guys take a lot of taxis, they store it and release the data as a public data set. And so you can actually get insane amounts of information about what people were doing. Actually, that URL in there is someone who is a data scientist who went through the data and showed all kinds of interesting things. He did like how long it takes to get to each of the 3 airports around New York City at the different times of the week, and a lot of fun stuff in there, where the hot bars are, right? All that stuff is available, and you can see the evolution of the data over time even. So it's 18 columns with no null values. It's all doubles, integers, decimals, and strings. Although some of the data is kind of ridiculous, like it's got the GPS data down to like, I think the inch level. Like, no, I don't think so. You actually have got way too many significant figures on that. Actually, you can kind of tell it looking at the other way. The data scientists produced graphs. The one on the left is where people got picked up, and the one on the right is where they got dropped off. And if you look closely, of course, you can see Central Park, which makes sense that you could see that outline. But you don't see holes where the lakes are. I very much doubt any taxis were picking up people in the lakes. And so I'm assuming the noise in the GPS data was responsible for a lot of that. But yeah, you can see the airport is one of the, that is a hot spot over there. Another really interesting data set is the GitHub archive logs. So every time someone does an action on GitHub, it produces a logged event, and they actually make that data set also available for free, conveniently broken down by day, by hour. It's a lot of fun to look through, actually. On the other hand, they don't give you the schema anywhere. I was like, okay, so now I've got megabytes, hundreds of megabytes of JSON documents with no schema. That's exciting. But it's got 704 columns with lots of structure and nulls, and a half month of data is 10.5 million rows. Now, I don't know about you, but I started going through the first couple and was like, oh, maybe I could build a schema. No. And so we actually wrote a tool that you can give a bunch of JSON documents to, and it'll produce a Hive schema. It does the kind of obvious things of, okay, this looks like JSON doesn't really have specific types. So a string can be all kinds of things. And so it looks, when it sees a string, it says, okay, does this look like a date? Does it look like a timestamp? And it'll put things into categories. But of course, if one value is a date and one is a string, it'll say, oh, it must have been wrong. It must have just been a string, and so on. So types will cascade up, and you come back with the union type of a whole set of JSON documents. That one was definitely amusing. We actually checked that into ORC because people found it useful and wanted to be able to access it. The schema in this case is huge. It's 12K of document. First I was going to put it on the slide. I was like, oh, wait. let's not make a reading test for these guys so that they can actually read the slides and without hurting their eyes too much. All right, the final table is a table from a customer that I have a tight integration with that I talk to a lot. And they store all their data in ORC, but they were totally willing to let me take their schema, and as long as I renamed all the columns. But of course, I couldn't get any data. So it's this actual sales table for a very large website that all of you know. And so it's at least a real schema. It's 55 columns with lots and lots of nulls, a little structure, but it's got a lot of timestamp strings, longs, booleans, lists, and structs. One of the things that you'll notice isn't here, it's a sales table. Actually, the first version of the sales table that they did used doubles. Okay, why do you not use doubles for counting money? Exactly, rounding errors. They basically ran queries, and depending on how they added it up, they got not completely, slightly different answers. Accountants really don't like it when you give them different answers depending on how you add things up. And so they've actually moved all of it to longs. Although, to be fair, their longs are actually tracking billionths of a dollar. So that's, I guess they're doing that for currency conversions to keep them accurate. But so this one we had to generate fake data, but we used the actual data attributes that match the underlying table. But those are the three use cases, the three use cases in terms of the data layout. So first we wanted to look at the storage. This matters. Sure, with Hadoop you can always add a new node and get more storage, but it still affects your costs, right? You still have to pay for those extra nodes, and so you want to be careful about it. ORC and Parquet, even without the top-level compression, do run length encoding in dictionaries. So if your column, you have 11111 1,000 times in a row, ORC and Parquet will just say, okay, they've got a 1 repeated 1,000 times. So even without the compression, that is turned on. They also have dictionaries so that if you have country name, it will store 1 copy and reference into the dictionary for that column. All of the formats have zlib and snappy, and as our QA guys like to point out, this quickly becomes a testing matrix from hell because now you've got 4 file formats, 3 use cases, and 3 levels of compression that you want to test. And yeah, that kind of sucks. Okay, so here's the size of the taxi. You can see the uncompressed JSON, really big. And that's, of course, because the metadata, the column names in the JSON, make it huge because it's really very dense data. And on the other hand, once you start compressing the JSON, it gets much better. You can see that in general, the run length encoding, the Parquet and the ORC do the best. zlib is your friend here with snappy in the middle. Now, zlib is a very, it's a tighter compression that takes a little bit more CPU to both compress and decompress. Snappy is faster, but doesn't compress quite as well. And so the first point is don't use JSON. And actually, you'll see it way better later, but snappy or zlib is a really good idea. And one of the reasons Avro didn't compress as well is because it uses a really small compression window. It's compressing, I think it's like every 20K or something pretty small. And Parquet did a little bit better than ORC. So, of course, being the scientist, I'm like, okay, why did it do that? And so because they're columnar formats, it was pretty easy to go into the files and say, okay, let's group the columns by type and see how they compared. So the orange in this case is Parquet and the green is ORC. So you can see the decimals are pretty similar. The doubles, ORC is much larger than the Parquet. The ints, they're about even, and then the timestamps are definitely the other way. So, of course, we wanted to figure out why, what's going on. It turns out that one of the performance engineers had realized that the compression, the tightest compression on the doubles was really hurting the decompression speed. And so he's like, oh, we'll tune it for doubles to make it compress not as hard, but make it faster. And so actually there was a reason for this, and it's almost exactly because it was designed that way by a performance engineer. Timestamp, on the other hand, kind of works the other way, because Parquet doesn't know what this is. It just thinks it's a 96-bit integer. And that 96-bit integer is the number of nanoseconds since January 1970. That's a big number, and so you get a lot of bytes. ORC, on the other hand, stores, it knows it's a timestamp, and so it actually stores it better. In particular, it picks an epoch of January 1st from 2015, which is a much smaller number. And it also does compresses the zeros off of the nanoseconds, because most people don't actually have nanosecond resolution on their data, which is why the ORC is so much smaller. All right, the sales side is interesting. Again, JSON is the largest, even with compression, which is surprising. Then Parquet and Avro and ORC did really well in that case, in terms of size. Of course, part of the reason is that it has timestamps and doesn't have any doubles. So exactly the factors that we saw last time played very well for this data set. One of the things that we still need to do is go back and validate with the original customer data what the benchmarks look like on their real data sets for that. And improve the random data number generate appropriately. Okay, now the GitHub sizes. First, again, notice JSON with none is huge, but all the nones are small, are big. Then it groups with all the snappies and then all the zlibs. What's going on here is that there's a lot of shared strings in this data, and so you end up actually with the zlib mattering most. One of the pieces that we need to investigate, actually, so the part of the problem why Avro is doing better in this case than ORC and Parquet is because the compression for Avro is going row major. So it sees the common strings like HTTPS:// over and over again. And so it compresses those really small. With the ORC and Parquet, because they're columnar, they start the compression over again on each column. So the compressor needs to learn those common strings over and over again. And one of the solutions that we need to investigate is using the Brotli compression. Brotli is a compression method that Google released that actually has a lot of the common web things built into it, like HTTPS. Okay, so what are the cases you guys actually care about? The first is full table scans, where you're just reading the whole table, all the columns, all the rows. And the important pieces here are basically how fast can you read the whole pile of data and whether you can split it or not, right? All the formats except for JSON are splittable so that you can have multiple workers working on each individual piece of the file. All right, so here's where JSON just completely dies, right? You can see how much slower JSON is because it's got to parse those strings over and over again for every record. That's really painful. Parquet was was a little bit slower than Avro, which was a little slower than ORC. Actually, in this case, you can see that the fastest one was ORC with no compression. So it was reading more data, but it was actually faster. And you can see that Gopal's speed up of compressing not quite as tightly was in fact worth it and made it much faster. So yeah, don't do JSON. I gave this talk once and someone was like, I don't know who Jason is, but boy, he sucks. Okay, so looking at the sales speed, here you can still see Jason is slow. The Parquet was slower than I expected, and then Avro, and then ORC. So we actually can see really see here the ORC was the smallest, and in fact it read by far the fastest. So the read format dominated the format, or dominated the speed, and I started to look at why that happened, and it looks like a lot of the difference is garbage collection, right? ORC was spending 0.3 to 1.4% of its time in garbage collection. Avro was less than 1.1%, and Parquet was doing 4 to 8%. So they're doing a lot of garbage collecting as they read. Okay, and GitHub got really painful for Parquet. It actually beat JSON for being the slowest to read. Actually, it's funny. I talked to the Twitter guys, and they're like, yeah, we don't use Parquet for this use case. We use something else because it's just too slow. And I was like, okay, why didn't you tell people that, though? Of course, they didn't want to because it makes Parquet look bad. Let's see, other pieces to notice. JSON is the next fastest, and then Avro and ORC kind of mix it up in the middle there. Garbage collection became even more important in this one because it's so highly structured that Parquet was spending between 11 and 13% of its time doing garbage collection. ORC was 2.1% to 3.4% of the time garbage collecting, which is still higher than I was expecting. We need to investigate that more. Avro, again, was doing really well. Now, one of the other pieces that we realized as a result of doing this is that with the really wide number of columns, ORC and Parquet ended up making really small stripes, which meant that they weren't compressing as well. You can see, actually, ORC took basically 19,000 rows, and Parquet took 88,000 rows. I should say that in both cases, we took the default values, and it really does show that we need to fix those default values because you should not be getting stripes that small. We probably want at least 1,000 times bigger, which is a lot. Actually, maybe 100 times bigger. Okay, so the next use case is to look at, if you just want 2 out of 200 columns, what happens to the speed? And of course, Avro and JSON are exactly the same, right? You could just use the numbers from the previous slide. But for ORC and Parquet, you see it gets much, much better. Actually, for the GitHub stuff, picking a couple columns got you down to less than 1% of the time to read. Sales, there are fewer columns, so taking a couple columns took you to a few percent. And then the taxi data, I don't know what the hell happened with Parquet, but it's relatively big. I suspect there's something going on there, but I'm not quite sure what it was. Okay, so those are the most common cases, but there's another really important case where a lot of the execution engines, actually most of them at this point, will do predicate pushdown and push your predicates down into your reader. So if you're selecting all your employees that were hired between 2 dates, that piece of the predicate can get sent down into the reader. Now there are limits to this. It has to be a simple column with constants on it. It can't be 2 columns. It can't be part of a join. So there are definitely limits to what it can do, but when it works great. In particular, you can pass that down, and now the ORC reader will use those indexes it has. It's got remember the indexes at both the file level, the stripe level, and the 10,000 row level. And it will not read any sections of the file that it doesn't need to satisfy the query. So it'll make sure that you don't skip anything that you could possibly need. The engine, of course, still needs to check, because if you get 10,000 rows back, it may just be that 5 of them meet the predicate, but so you need to go through and check at that level to make sure they work. Now, the Yahoo guys had 2 teams, one that was working on Spark and one that was working on Hive and was testing TES and doing comparisons. So they were running some queries through, and in one case they got really surprised, because in most of the cases, sometimes Spark was faster, sometimes Hive was faster. It kind of depended on what the query was and how well each of the optimizers did. But in this case, Hive was coming back much, much faster, even on the second and third run, which normally Spark, because it's got it cached in memory, does really fast. They figured out what was going on was exactly predicate pushdown. They had a sorted column, and in fact, the predicate pushdown meant that even though Spark had it in memory, it had to read all of the 80 terabytes or whatever of the data to find what it was looking for, because Spark doesn't have any indexes. On the other hand, ORC, it read the file footers and said, oh, there's only one file I need, and there's only one piece of one file I need. So it only had to read the 10,000 rows in a single mapper, and then came back with the result very, very quickly. All right, so what does that? Parquet obviously has predicate pushdown too. They added it because ORC had it. Although one of the differences you should understand is that the Parquet predicate pushdown only works to the file in the stripe level. So they don't have the equivalent of the 10,000 row indexes. So you only can cut out big chunks of the file. One of the pieces that's important about predicate pushdown is that it lets you lay out the data better. For example, at Yahoo, there was one group that had all the different properties, and there's like thousands of properties, and all the different countries, and they wanted to partition the data based on those too, so that they could do the partition pruning much better. But what that meant was they could set up the partitions fine for the US, but for the Netherlands, it was a really small set of data, right, for each of the different properties. And so that meant that you had some partitions that were huge and some partitions that were really small, which really kind of sucked for any kind of distributed processing. We actually convinced them to, instead of partitioning on it, to sort on it, and then predicate pushdown could make the file just as efficient to read as if you actually were doing partition pruning at the higher level. One of the pieces that we added a few years ago is bloom filters. Bloom filters are big enough that you can't do them all the time. So you need to consider which ones you're going to do them on. But there are a lot of help for non-sorted columns. In particular, if your data is sorted by time, which is very common, and you want to search by user ID, then bloom filters would be great for that, because then if you're looking for a particular set of users, you can use that to filter out which data gets read. Okay, there's also metadata access. Because as we're writing the data, we might as well store the file attributes in the footer. So we store the number of rows, the number of whether they're nulls, the min, the max, the count of each of the columns. actually store the sum also. And so that stuff you can grab in basically O(1) access because it's all at the very bottom of the file. Okay, so first a disclaimer. Everything changes, right? All these projects are viable open source projects, and so they've got communities and they're making changes in them all the time. And so always take updates into account when you're looking at things like this. If you have complex tables with a lot of common strings and you don't need the column projection, Avro is a pretty good fit. Actually, it does really well. It's very fast. It doesn't generate much noise, doesn't need much memory, and so it does really well. For the other tables, ORC with zlib did really well, but please do experiment with the benchmarks, which are available in the ORC project. Actually, they're a pull request right now. I'm going to commit them this week, though. Other fun stuff. Actually, as part of doing this, we built pieces of tools to convert files. Mostly that's not that useful. If you're going to really do it at scale, you would do it with Hive, and because then you can get a MapReduce job to read the data in one format and write it in another format. But for playing around with it or making changes, it's really useful. For making tests, it's awesome. Actually, in the tool store, we also put the conversion from ORC to JSON and from JSON to ORC so that you can convert either way, because that seemed really useful for a lot of people. We also created a random parameterized generator that you could specify the properties of your data, and it could generate it. That's what we used to generate the sales data. Okay, so that's my presentation. Any questions? Oh, come on, someone's got to have a question. It's in the ORC project. Yes? The costs of going into the HBase will probably make it different. I haven't looked at the case. Oh, sorry, the question is, would the cost be different if you were storing the JSON in HBase? There's going to be a lot of overhead talking to the HBase and pulling the data back. But that's going to provide a different set of trade-offs. You'd really need to benchmark it to see what's going on. My hunch is that you're still going to spend a lot of time doing the string processing and burn a lot of memory. Probably, yeah. Yes?
What would you recommend when you're running a generic project? Would you just take one of those files, or would you always do a benchmark for it?
I would say that in general you want to look at, you typically want ORC or Parquet. You also want to, for the most part, keep it to fewer file formats rather than more. And so once you get started with one, people usually just keep going. They're close enough, although if you're, like I said, if even Twitter, if in their highly structured case, they're like, no Parquet. Was there a question over here? Yeah. So yeah, there is one. So this was mostly how data gets accessed from Hive and MapReduce. Spark actually has added a bunch of optimizations for Parquet that make Parquet work much better for Spark. Now, to be fair, we are absolutely working on addressing that and putting that in for ORC too. So that's very high on our list of, we're extremely aware of that one. Yes? I'm sorry, what? I'm still not hearing you.
Why did you see garbage collection?
Oh, I didn't actually play with the garbage collection algorithm. So this actually was mostly done with the standard garbage collector. You're right, I probably should have played with the other options. That's a good point. Thank you. All right, well, thank you very much, guys.